Thank you all for showing up. I'm glad to see there's still some interest in Kubernetes. This is a very basic introduction to Kubernetes, kind of what the components are, why, how it does what it does, why we use cloud for Kubernetes, and then I will walk through a demo of deploying a Kubernetes cluster on an EC2 instance, showcase how we go about deploying applications to Kubernetes, talk about exposing of services, and hopefully at the end of the day, everything should work and we'll get a web front end that demonstrates that. Before I get started, how many have played with Kubernetes at all? Okay, production, if it's a lab, raise your hand. Production? Oh, okay. Well, you guys can go up and teach the class then. This is probably a little bit beneath, but that's good. So a lot of this will be new for everybody, and hopefully it's a fun session. You get a little bit out of it. My name is Quinn Snyder. I'm a technical advocate with Cisco Learning and Certifications, and I know my subtitle says, if you think Docker Compose was tough, this is actually a fairly once you learn the basics of Kubernetes, it's fairly easy to manipulate and get around. And for anybody who is looking to attempt their DevNet expert exam, Kubernetes is a piece of that with some of the manifests for deployment and things. So this will be a good primer for that. So we'll talk about Kubernetes in the background, how it came to be, what it, why it was developed, and how it actually is a good thing despite all the overhead. We'll talk about the fundamental components of Kubernetes, and then on top of that, we'll also talk about what differs from when we talk about vanilla Kubernetes, or you talk about the Google, I guess it's now the Cloud Native Foundation, the basic vanilla installation of Kubernetes, and contrast that to what actually exists inside of the cloud provider and what they do on top of that. I'll talk about how you actually can lab Kubernetes very simply. You can do it on your laptop. You can do it in a cloud instance just using a simple EC2 or equivalent. And then I'll do a demo, and we'll wrap it up with some conclusion. At the end of this, all the source code that I use for this is available on my GitHub, and there'll be a QR code where you can grab that as well if you would like to play with it on your own. So for background, Kubernetes was a Google project, was originally released in 2014, and is now the Cloud Native Computing Foundation project. So when it was removed from Google, the CNCF, they have a whole open source governance committee from release to the SIGs to all the different pieces, and every new release from like, I think right now they're at 1.32 or 1.33. Each of those releases has to go through a large governance process for release. Now, I say that there's the Kubernetes release has its governance, but there's a lot of underlying technologies that make up Kubernetes that also have to fall in line. So there's very strict version requirements of the underlying containerd.io and all the application, or all of the supporting infrastructure pieces that run on top of it. So there's very, very tight requirements for everything to work together. And it is based in Go. So all of the tooling that is native to Kubernetes will all be written in Go, which is nice because it's fast, it's web native, and all those kinds of things that come with that. At its core, and the original the development for Kubernetes was a platform for development and operation of stateless microservices. So we talk about microservices being front end or application containers that are communicating with each other via some sort of mechanism, generally REST APIs. So the containers themselves don't hold any state. They're simply processing the information that they're received and pass it along to another container. I say mostly, or I say stateless in parentheses now, because now we have things like databases that are being deployed to Kubernetes. We can have AI workloads that have large language models being deployed to Kubernetes. So it's really become a platform du jour for a lot of different things, but at its core, it's still running containerized workloads, and Kubernetes provides the management and oversight over the top of it. It is completely API driven. So when I deploy a Kubernetes node, it has its own Kubernetes control plane node that will handle all the API requests. And as today, I will be interacting with kubectl, which is the kind of de facto CLI tooling to interact with Kubernetes. Every kubectl command will also is actually translated to an API request to the control plane node. So even though I'm interacting via a terminal, I'm only sending API commands to the Kubernetes control node via the translation and the tooling built behind that. And the most important part, it's supported amongst every major cloud platform provider. So AWS, Azure, Google, Alibaba, Oracle, if you're not a real cloud provider anymore, unless you have some sort of managed Kubernetes, and we'll talk about why that's important. Now, like I said earlier, there's a lot of things that are underneath the covers of it, but it's really just Docker. Well, it used to be Docker, and now it's containerd.io all the way down. So when I deploy Kubernetes, I have a variety of nodes, and we'll talk about the nodes in a slide. We have a control plane node that handles all the API requests and the scheduling and management of the containerized workloads, the deployments, the applications that ride on top of those of the worker nodes. Those worker nodes receive the containers, or in this case, in Kubernetes lingo, it's pods, across those. The scheduling service in the control plane splits those containers across the pods. So just because I have an application that may deploy 30 containers does not mean that those 30 containers will all be deployed to the same server. The control plane node will handle all the scheduling based on resource management and communication across those servers and deploy those containers where they are suited best. You can set some affinity levels, so maybe there's things that need some tighter requirements for communication, interprocess things. You can set affinities for certain containers to a different to the same node, but for the most part, that control plane node will handle everything. So it handles the failure recovery. So if I lose containers, if they fail, the server dies, whatever, it will rebalance and restart those things. But everything that is bounced across that is handled by the control plane node. Like I said, interacting with Kubernetes, you use the kubectl. There are other tools that can be used, but kubectl is kind of the de facto standard there. We don't use the Docker CLI. So even though these in a past life we're running in Docker, we don't interact with the individual containers with a Docker CLI on those worker nodes. It's all driven through the scheduling node or the control plane node and the scheduler through kubectl. The nice thing about that is because it's API driven, if I have a .kube config sitting on my laptop pointing to a control plane node with the appropriate key, and I'll show you what that looks like, I can use my laptop as the control as the API endpoint to control that Kubernetes deployment. So I may have something sitting in AWS. As long as I have that AWS IP and the large key that's generated out of the kube config sitting on my laptop, I can manage that Kubernetes resource just from my laptop because it's all API driven. I don't have to be sitting on the control plane server itself via SSH or something like that. Let's see if there's anything else I want to cover here. No, we're good. All right. So from a terminology perspective, this is taken directly from the CNCF Kubernetes like fundamental page. I have a link probably in another slide. So at its basic architecture, you have one or more control plane nodes. And so that is sitting right here. So we have one or more control plane nodes. That control plane is handling the APIs and does not handle any workloads by default. So that server is just sitting there to handle the scheduling, the resource management, and the API gateway to be able to communicate with all the different worker nodes. You can set up for like a lab environment. So I know a lot of people like to use like a stack of Raspberry Pis or something like that to build their own Kubernetes cluster. You don't want to dedicate one Raspberry Pi for a 3-node cluster. So you can actually taint your control plane to run workloads in a lab or kind of a testing environment. But in production, you'll have the control plane node will only be handling the control plane requests. Like I said, that handles the scheduling, the resource management, and things like that. So it's not a node, and I should have done quotation marks there. Control planes are not nodes, and a node is what's actually running those workloads. The nodes themselves are just grunts. In fact, if you go through the getting started guide with Kubernetes, if you roll your own, it says to disable everything that makes your computer smart. So you'll disable things like RAM management. You'll disable things like swap space. You want that piece of compute to be nothing but a beast of burden to run the workloads. All of the intelligence is handled right here through the control plane nodes. So that's how we get that resource management. On top of every worker node that is running, there's a communication that goes on with the control plane to say, here's the status of my memory, here's the status of my storage, my CPU cycles. All that's being intelligently reported back to the control plane to handle that schedule piece. And actually, this is the control plane. I'm sorry, here's the nodes over here. So you'll hear them called kubelets. We've got proxies and things like that. This is the control plane side. There's the node side there. I tried to get around the eye chart of terms. I'm really sorry. I couldn't find anything that incorporated this. So these are the common, when you're talking to someone who knows Kubernetes, these are common terms that they'll use. A cluster is just a set of worker machines or nodes. So we'll talk about Kubernetes clusters. So a cluster is the control plane plus all the worker nodes sitting there together. They're bound by that control plane. So I can have one cluster and I can have another cluster over here. My kube config that works in cluster A will not work in cluster B unless I have that copied over to my machine. A deployment is just as it sounds. It's an object that manages the replicated application. So we'll talk about deployments when I deploy something to my Kubernetes cluster, but that's just, think of it as I've deployed an application, or I've deployed something in all the supporting services. So if we look at a 3-tier app, we may have a web front end, an application, and then a database. Those 3 pieces tied together may contain multiple containers for each, but I manage them as a single deployment. So my manifest that I send to Kubernetes that dictates, here's the stuff that needs to be created, we call that a deployment. Now, generally, we put different deployments in different namespaces. For the networking amongst us, think of a namespace as a VRF. Because each, in a perfect world, each deployed container will have a unique name. There should be no collisions. But we need to make sure that we can guarantee that, and so we separate things inside of namespaces. So generally, we'll have a namespace for our overhead control stuff, and we'll see that when I deploy things like with Kind and Calico, and then the Sock Shop app. Each of those will be in a unique namespace that is separate from each other. So while the names will not overlap, we say all of the things that are associated with this deployment may go into this namespace. We talked about node, which is just a worker machine, and a pod is just a set of running containers. So like I said before, you may deploy multiple copies of a single web front end. So we may have a distributed web front end with ingress web front ends on each of those nodes. We may deploy 3 copies of that web controller. Those 3 containers may be separate, but we call them a single pod because you'll see the numbers of containers that are developed there. So a pod is just a set of running containers that all perform the same function. And I'll talk more about that. A lot of this is kind of in the abstract until we get to the demo. And then finally, a service is a method for exposing a running application from within a server. So we talk about services. Think about when you're running Docker locally on your machine, right? We have a container. That container is running inside of that isolated Docker pod, right? I have no access to that container inbound from my local, even on my local machine, I can't get to that container. I have to use the -p mapping or expose in the Docker file and then map that to an external port before I can have inbound communication. Because we're running Docker or container.io underneath the hood, the same thing applies for Kubernetes. There's some internal networking, internal communication that happens between all these pods that are running on the Kubernetes server, but I can't get into them unless I expose some service. So things that expose those services for the cloud, we can have load balance services, we can have ingress IP services. If you're running locally, we can run things like Metal LB to get that same functionality. We can expose node ports, which is what I'll do for the Sock Shop, basically to allow me to access those things from the outside inbound to that Kubernetes cluster. But by default, nothing is exposed outside of that Kubernetes cluster unless I tell it that it is exposed. And down here, the Kubernetes.io, if you just go to that page and go to /docs, everything that I've talked about, all the images and things are all up here as well. And I'll hold on until he grabs that picture. All right, we're good. And I will a copy of these slides will also be posted in my GitHub repo with all the source code as well, so we don't have to worry about, oh, he moved too fast. Now, I mentioned earlier that vanilla Kubernetes is plain, and it is just vanilla. So Kubernetes is literally, I've deployed my container runtime environment and the Kubernetes pieces on top of that. That's it. So nothing is included with that deployment. So things like overlay networking, communication between servers, that's not included. Distributed storage. So if I want to have a storage volume that may move between different hosts, that's not included. Any observability, so you hear a lot of things about service mesh, Istio especially, that's not included. It is literally run containers and control them. So many projects exist for nice to haves. So talking about distributed storage, Rook and Ceph are 2 very common applications that ride on top of Kubernetes to provide distributed storage and inbound storage access and permanence inside of a Kubernetes environment. We have Calico and Flannel, which provide overlay networking. So if I have multiple nodes, by default, they can't talk to each other. Calico and Flannel, two different projects, allow you to communicate and provide distributed networking across those nodes so they can communicate and share information. Istio and Console are two different service meshes. So a service mesh, think of it as a sidecar. I deploy a container, and there's this little thing bolted onto it that gives me analytics and data out of it. So things like API usage, things like connection states, things like that we want to observe with things like App Dynamics, or visualize using Splunk, or maybe it's just the Istio control panel. All of that is an additional add-on that you have to deploy on top of Kubernetes. And I'm not to be vain, but I am quoting myself here. Every engineer should install bare metal Kubernetes exactly once. Because after you've done it once, and like I said, adding all those overlay things on top of it, after you've done it once, and how many folks lived through the early days of like Red Hat with RPM dependencies and having to resolve all those things? It will feel very familiar to that. You will be stuck in this Kafka-esque environment where you cannot get out of it. You'll deploy it once, and you realize why we pay for cloud, because that's a pain. So now that we've talked about the components, let's talk about the easier ways to Kubernetes. There's a set of local Kubernetes tools. MicroK8s is one. It's made by Canonical. It's a lightweight, and it usually runs on the very testing or edge deployment use cases. So if I've got some very lightweight, like ARM compute that sits at a remote store, or maybe I've got an Intel NUC, I may use something like MicroK8s to deploy that. Makes it very simple. Minikube is another one. It focuses on speed and compatibility. So like I said earlier, Kubernetes has very tight version requirements for not only the Kubernetes control planes, but also the underlying infrastructure like containerd.io and things like that. So generally, I'm in like this very tight matrix of I can use Kubernetes 124 with this version of Docker, with this version of this, and this version of that. Minikube kind of handles a lot of that for you. And the other thing is that Kubernetes support is generally 3 years per version. So within 3 years, you've got to update to the next version. Minikube allows you to deploy really old versions just by setting a flag. So if you need to go back and do some regression testing, you can do that very easily with Minikube. My favorite one is Kind. It's Kubernetes and Docker. So it's the closest emulation that I found of a local Kubernetes or a production-grade Kubernetes environment. So if you think of it as kind of an inception level piece, I've got I run Docker on top of my host, and then I deploy individual Docker containers. Those Docker containers emulate a Kubernetes cluster that I then run the control plane on top of. So we've got like 3 levels of turtles all the way down, but you can do some really cool stuff with Kind. And I found it to be the most forgiving of those lab environments, at least in my experience. There's also Docker Desktop that you can spin up your kind of a basic Kubernetes. I think it's a single node, so you can kind of get that same API look and feel. I've not played with that as much because I like having a multi-node deployment there. For production, people use MicroK8s for the, like I said, for the edge or that lightweight compute. K3S is a really a nice tool as well, because that's kind of batteries included. If I'm running a larger cluster on top of VMware or things like that, I'll build 4 or 5 different VMs and deploy K3S on top of it, and it's all kind of batteries included, ready to go off the bat, so I can do some decent testing. A lot of people use K3S on top of their Raspberry Pi clusters as well. We can do OpenShift, or you can pick a cloud provider, and I've noted these are my favorites. The cloud provider is really easy. I just request something from Amazon EKS, define how big I want the cluster to be, what my parameters are, and I can use Terraform, and boom, I'm off to the races. But you do pay for it. Although, like I said, if you deploy vanilla once, you'll realize the cost is worth it. Or you can roll your own, and like I said, don't do that more than once. If you want to know more, Chapter 7 of the DevCore Official Cert Guide, it's a book I helped co-author. I dive really deep into Kubernetes in that book. So if you have that, I'd be more than happy to sign it as well. So with that, I will go ahead and demo. I'll leave this screen up for a second if you all want to take a QR code, and I'll also bring it up after. I'll leave it up after the presentation. But it's just github.com/qsnyder/Cisco U2001, which was the original. Actually, I think this one is 2001. We change some of the Cisco U session codes every now and then. So are we good? All right, let me scroll over here. So all I've done is this is just a very simple Amazon EC2 instance running with really nothing on there. So I have Docker. I have Docker running on here because I'm going to use the I'm going to use Kind to deploy this, but it's just a real simple installation of Ubuntu 22 something and Docker on top of it. So let me go into the demo. And let me go into cluster. So in here, I have a couple of things. Let me cat kind config. So this is just defining, written in YAML, this is just the definition to build my kind cluster. So you can see I have one control plane of 1, 2, 3 worker nodes that are there. I'm running a certain version of the Kubernetes control on top of that, so version 123.10, a little bit older, but it still functions. I've also disabled a lot of the default kind stuff because I wanted to talk about some of the overlay things that aren't included and show you what can happen before and after the deployment. So I just have this kind config.yaml, and I'm just going to do, I'll show you the cluster build shell script. All I'm doing is saying kind cluster create. I've given it a name and I've given it a config file, and it will build that cluster for me. So let's cluster build. So deploying to kind, you can see it's going to make sure it has that image already, just like it would any other Docker pull. It's going to build that, and hopefully this works quickly, because I wanted to show this process. But it's going to prepare each of the nodes. So it's going to build that control plane, build those worker nodes, make sure everything is ready. It's going to install some of the default overlay stuff with kind to make sure that it communicates. But again, I have not enabled that overlay networking piece of it. The joys of live demos. Perfect. So it's going to write the configuration. So that means it's going to write that kube config configuration to my system, and then it's going to start the control plane node so that I can then schedule those resources and deployments and things like that on top of Kubernetes. And it's going to handle, like I said, some of those things like the storage. The distributed storage. It's going to then take those worker nodes and then join them to the control plane. So that is not done automatically. Normally you have to do that by yourself. So each of those worker nodes has to be told that it is part of that control plane. So it'll do that. Cloud patience, man. Perfect. Okay, so now we have this. Now we have this Kubernetes cluster. So you can see I have this kubectl get nodes. So there's my kubectl command. Get is just a syntax. There's a lot of syntactical things with Kubernetes, the kubectl command. And then nodes are just saying, okay, here's the nodes that we have there. Now you can see that each of those is not ready. And that's because even though they're deployed, I have no way of communicating across those because I disabled that overlay networking as part of my config. Luckily, I have got a couple of things here. So in this case, I'm going to use Tigera, which is Calico, which is the overlay networking. So if I do, let's see here, kubectl get pods. You can see here is what has been deployed already as part of the kind deployment. So you can see I've got a control plane, I've got some Kubernetes proxies, the scheduler, the manager, and then I also have this core DNS, which is kind of that service reachability across that control plane. Or between the worker nodes, I should say. Because I do not have that networking enabled, that core DNS is failing. I can't have my worker nodes communicating with each other just as I did before. So I'm going to, what is it called? The cat Tigera operator. And this is a long YAML file, but this is what a Kubernetes manifest looks like. And so, without getting into too many details, there's a lot of things that are going on here. You can play with it or look at it as I go through, or with the source code later. Essentially, this is saying, here's some containers that you also need to download and install as part of a deployment in the Kubernetes namespace. And on top of that, here's how we're going to tie them all together. So we're going to do a kubectl create f Tigera operator. So I've just deployed an application to Kubernetes. I say take this manifest file and deploy it to the Kubernetes control plane. Kubernetes receives that manifest and says, I know what to do with all these pieces. I'm going to download some containers. So if I look here again to this get pods all namespaces, we can now see that we have this Tigera operator that is now running. I've deployed that container there. We still are pending some of these running here because there's one more piece I need to do. You can also see over here on the side, I have this new namespace called Tigera operator. So I've created a new namespace for that operation to occur. The next piece is going to be the custom resources. So kubectl create f custom resources. So now I've added a couple of new pieces here. And hopefully, yep, we can see that we have these Calico nodes that are now creating. This container creating says I'm reaching out to the Docker registry. I'm downloading those containers. Some of these are in the init state, which means they're initializing. I've already downloaded them. I'm spinning them up. And hopefully here, it's taking a second. So now we can see that this core DNS container is now being created. It has the reachability via that overlay networking. It's now saying I have the reachability between all my different worker nodes, and I'm going to create those containers and make sure that everything is hunky-dory. And finally, hopefully, this always runs a lot faster when it's at my house. Okay, we can see that we're starting to get a lot of these, so that core DNS server is now running. We have some other stuff within the Calico system namespace. And we share, yep, we're now running now. So I can do a kubectl, get namespaces. Here's all the namespaces that have been created. Some of them are part of the kind deployment. Some of them I've created, like the Tigera operator and the Calico API server and name system. But now we have, and you can see that they're started just a few seconds ago. So now we have our Kubernetes cluster that's up and communicating. Inside of here, I have what's called Sock Shop. So Sock Shop was written by this company called Weaveworks to test their web microservices front ends. It has since become kind of this open source thing where if you want to deploy an easy application to Kubernetes, you just deploy Sock Shop. And I have a lot of demos of that in the DevCore OCG. But what I'm going to do here is I'm going to do a kubectl, create sockshop.yaml. So this is saying I'm going to create all of these different containers inside of my Kubernetes environment. So and they've named them appropriately. So I've got this whole microservices front end, from an API web front end, application services, database services, all those things that are required, and all the way to payments and checkout, and all these things are different containers that get created as part of this manifest. And it's a very lengthy one. You can see I've deployed a new namespace called SockShop as part of that deployment. I could have deployed it in any namespace I wanted to, but it creates one called SockShop. And I'm going to do a kubectl get deployments, because that SockShop is a deployment. And I want to look across all namespaces, just so you can see. So you can see I have all of these, most of these containers are running. I have a few, like the orders and the payment and the queuing and stuff are still being built. So hopefully here shortly, those will come up. But you can see that I'm able to check these different pieces. So I treat the Sock Shop and each of those things, the cart, catalog, orders, etc., is a deployment. That means I can restart each individual component of that microservice as needed. I can redeploy, restart, etc. Okay, now we're all up and running. But if I do a kubectl get services, you can see that there's a lot of stuff that's here. Here's a cluster IP. By default, we have a lot of overlay networking and IP addresses assigned to Kubernetes. But these cluster IPs, they're all internal. I can't access them. They're part of that Kubernetes cluster. And just to show you that that's the case, I have what's called caddy. Let's see here, caddy command, which is just a reverse proxy. And what this is going to say is take anything inbound from port 8080 and redirect it to the control plane port on 3001, which is the port that the Sock Shop runs at. So if I do a bash caddy command.shell, and I go to my AWS resource at port 8080, we can see that we have nothing there. This page isn't working, no response. All right. I've one final piece of this demo, and it's the Sock Shop node port. So like I said before, by default, each of those containers is running isolated. I can't get into them unless I expose a service outbound. The cloud providers make that really easy with load balancers or ingress proxies or things like that I can set up. But I don't have that availability in kind. I'm not a cloud provider. I'm just some jabroni running it on my local system. So what I've done is I've created a node port, which is basically like a NAT translation, if you can think of it that way. I translate from one inbound port and push it out to another one. So I'm exposing port 3001 here, and I'm moving it to port 80 on the inbound web front end service of the sock shop application. And you can see that if let me do this kubectl get services namespace, or all namespaces. We can see there's nothing fancy there. They're all cluster IPs. I'm going to do a kubectl create f sockshop node port.yaml. It creates that service, so we can see there's a difference there. It's now a service, and it's called front end. So if I go back to all namespaces, you can see there's one front end node namespace to sockshop on port 3001, or 30,001, forwarded to port 80. So now if everything works, because remember that original definition was exposing 3001 to port 80, and then my caddy exposes 3001 to 8080. I know it's like Inception there. If I go to my AWS web front end and enter again, I have sockshop. So that's how Kubernetes works, and that's how it's deployed. We have a lot of different containers that work as services. Each of those services is managed through a manifest. Those manifests are deployed via kubectl apply or kubectl create. From there, it gathers the containers and stitches them all together via those overlay pieces that are included either in the cloud provider or with your deployment of choice, like I use Kind. I then need to expose any web front ends out of that using node port. Or a cluster IP or things, or sorry, not cluster IP, but load balancer or things like that. And once everything is working, we can have a microservice-based application running in the cloud or wherever you want it. So I know I'm a little over, but what I will do is I will go back. I'll leave that up. If you have any questions, I'll be around for a little bit. I do have another presentation at about an hour and a half over in the DevNet zone, but I'll be around to answer any other questions about Kubernetes, Docker, or anything like that. So thank you so much for your time.